Okay, let's do this. What do you say? Now you're leaving?
No, I'm just doing things.
Oh. Wait, I know it's taking a while, but. Okay. A lot of you haven't had chemistry yet, right? But did you have chemistry in high school? Do you remember the ideal gas law? Larry?
Oh my gosh. How's a cadence?
PV.
What?
Doesn't have a cadence?
It's got, well, yeah, I mean, yes and no, yes. Or an R. PV.
Equals.
Yeah. Too bad Amber is, well, because she knows it. She's in chemistry.
Pressure.
PV equals nRT. Everybody remember that thing?
Yeah.
No, yeah? No. Did you take chemistry in high school?
Yeah, sophomore year.
What's N? Anybody remember? Okay, P is pressure. Right, the pressure of the gas. V is volume. Anybody remember what N is? Little n? They love this thing in chemistry. It's named after a little animal.
Moles, yeah.
Moles, the number of moles of the gas. R is the gas constant. T is
Temperature.
temperature in Kelvin. Right, so PV, we're going to see where this comes from. In chemistry, when you take chemistry, they're just going to give it to you. Like, oh, and then you're going to use it. But we're going to see where it comes from. Right? Work out the details. Because we're in physics, we're better. That's on video now. Okay. Physics is fun. All right, so if you remember the other day, we were talking about linear expansion, area expansion, volume expansion, right? So if we looked at volume expansion of a gas, we didn't look at that, but it's interesting. So this is kind of the early experiments that we're learning about, expansion of gases. And they were measuring the volume of a gas, this is temperature in Celsius. If they had some gas, right, they would find it would expand. The formula, of course, V equals V naught 1 plus beta delta T, right? And we're going to start at T equals 0, our gas. T equals 0, and so it expands, right? And then you can extrapolate back this line, because it's a linear expansion in T, right? It goes up, and if you extrapolate back, find something interesting. What would happen right there? At that temperature, what happens to the gas? According to this graph. Yeah. 0 what?
Volume.
0 volume. The gas has 0 volume. That's weird, right? This is the first insight into absolute zero. Right? Because all of a sudden now, the gas is 0, and this temperature when they measured, when they worked out the extrapolation was 273.15 degrees Celsius. Oh. And then they looked at other gases, and you extrapolated them up, and like that, and you extrapolated them back, and they all seem to come back, no matter what volume of gas you started, it always came back to 0 volume at 0 degrees Celsius. Right, negative 273.15 degrees Celsius. So this was the first indication of absolute zero was studying gas expansions. And the beta, remember what beta was? The coefficient of volume expansion, right?
3 alpha, right? 3 times alpha.
Right, if it's a solid, it's 3 alpha. But a gas, of course, it's not a solid, so it's just beta. But we can figure out what that is. So let's work this out. So if we look here at 0 volume, right? We have V final is 0. Initial volume 1 plus beta. Now this is T final minus T initial. But what was our T initial for these experiments? Right here, which is 0, so I can ignore that term. So I have 0 equals, well, V naught can't be 0, right? That's the volume of the gas to start. So this thing has to be 0. 1 plus beta T final. So what does that tell me beta is? Negative 1 equals beta T final, or beta equals minus 1 over T final, or minus 1 over negative 273.15, or 1 over 273.15 degrees Celsius. That's what beta is. They found that's true for all gases. They have the same beta. which is interesting because solids and liquids, they don't all have the same expansion, coefficient of expansion, but gases seem to. Why would that be? Think back to chemistry, physical science. You ever take physical science your freshman year in high school? And thinking back, you had the model of the different phases of matter or states of matter. You had solids, liquid, and gases. And how did you picture those? You remember? What do you treat a gas like? No?
Was it like an exponential curve?
Okay, there's a curve. Yeah, there's a curve.
Yeah.
So good, we're going to see that curve in a minute. Let's pull up a simulator. I'm going to erase the board. And let's look at the simulator, and this will give us the picture of a gas. All right, there we go. What do you see?
Molecule.
Molecules moving around, bouncing into each other. Right? This is a picture of a gas. Right? A molecular picture of what's going on, a model of a gas. What about a solid? We talked about solids before. We had molecules, but what was different? They're connected to their neighbors by bonds, right? So it's that bonds that changes the different coefficients of expansion, right? Some bonds are tight, some bonds are weak. That's going to affect the coefficient of expansion. Here, though, the molecules are bouncing around. They don't have any bonds, right? So that's why all the gases have the same coefficient expansion, because there's no intermolecular connection. Right? Does that make sense, everybody? We're gonna treat all gases the same. All right, this is going to get us into the ideal gas law. Right? And you can see we have molecules. This is the speed diagram. Here's that exponential you were talking about. Right? This is the speed here. This is the number of molecules. Some molecules are moving fast. Some molecules are moving slow. Most molecules are over here. Right? There's this curve showing you the distribution of the speeds. Right? So that's what Mary was talking about. Okay, so we're going to derive that PV equals nRT, the ideal gas law. Okay? And we're going to use physics. Physics 1 principles. All right, let's pull up a white screen. We'll come back to that. Okay, so we're going to use two assumptions, or two broad categories of assumptions. We're going to use kinetic theory, and then we're going to use the assumption of ideal gas law. And I've written them up here on the board. So the first two is just the assumptions of kinetic theory. Yes?
Do you want us to write these down? Like, are we going to need them later, or is this just the...
Yeah, these would be good concept questions. Don't you think?
What were the two different categories?
These were the kinetic theory. And of course I can't spell, you know how that goes. And these are ideal gas. First, kinetic theory, large number of molecules. What do you think we're talking about? It's like 50 molecules a large number. No. And even in our simulator, maybe we had 100. Is that a large number? When we're talking about molecules? What are we talking about when we say large number? What size are we talking about? Think about chemistry.
Like millions, billions, trillions.
Millions. More than millions. More than trillions. Think of the little animal. The mole. What's 1 mole? Anybody remember?
My coach is calling me.
Your coach?
Yeah.
Oh, they want to take physics?
You know, more. You just gotta take that number and like multiply it times 10 to the...
1.66 times 10 to the 23.
Yeah, 6.022 times 10 to the 23rd. That's a lot of molecules, right? That's what we're talking about. We're talking large number of molecules. We're talking huge. I mean, there's billions on billions on billions, right? That's just a mole, right? So we're talking about that large number of molecules. The other assumption is we can use average behavior. That the overall properties of the system are described kind of by an average of what's going on. Some are going fast, some are going slow, but it's the average type of thing that's important. All right, does that make sense? It gives us our large scale measurements. So we're going to do large scale measurements. We're going to measure temperature, volume, pressure. We're not going to measure every molecule. How could you? Right? You know what I mean? This many molecules. You can't measure that many molecules. But we can get large measurements. Okay? So these are the kinetic theory assumptions. These below are the assumptions for an ideal gas. Okay? So these are what make a gas ideal. Not ideal and nice, but just easy to calculate. Okay, that's what I mean. We're going to treat all the molecules the same. Is the air in this room an ideal gas, according to that assumption? No. We would die. Right? What is this gas? What is the main gas in the room? Anybody know?
Oxygen?
Nope. Nitrogen. 70% nitrogen. And then I've got 20% something like that oxygen. We got carbon dioxide. We probably got some heavier stuff. We might have some methane, maybe someone ate breakfast burrito. Right, so that was a joke. Afraid you guys are so serious. So we're going to treat all the molecules the same, but they're not really. But it's a good assumption. Okay, so all molecules the same. The volume of the molecule is much less than the volume of the room. Pretty good assumption, right? Molecules, molecular size, the room's big. I don't have to worry about the molecules taking up space in the room. Now, you can relax these and you get different equations than PV equals nRT, but we're going to assume that. Math term, isotropic. Space is isotropic. What do you think that means?
Equal.
Equal, the same. Tropic is space. What we're saying is X, Y, and Z are the same. There's no preferred direction for our gas. Now, think about the atmosphere. Does the atmosphere have a preferred direction? Is there something different in one direction for the atmosphere? Yeah, what does gravity do? Yeah, it pulls things down. So what does that mean in terms of the gas? The atmosphere is a giant gas. It's denser at sea level than it is up in mountaintops, right? You go up high, you need oxygen deprivation, right? Anybody heard of this stuff before? Right? You gotta get used to it because the density is different. We're gonna assume the density is the same. We're not gonna say that our container is gonna be small enough we don't have to worry about gravity, right? So isotropic. Hard spheres, we're gonna have elastic collisions. What does that mean? Physics 1 coming back. What's an elastic collision?
There's like energy left over after the.
Perfectly elastic?
Yeah, perfectly elastic means the energy is conserved in the collision.
Conserved.
Is that what you were trying to get at?
Yeah, right.
Right, so when these molecules strike each other, they don't lose energy in heat. They just bounce off each other, right? When they hit the container, they bounce off the container. Now, this doesn't happen in reality because what happens? You got two gases, sometimes they're going to do chemical combinations. You're going to get a mixture, and of course that's going to do what? Chemical bonds are going to take energy, so you lose energy. So we're going to assume there's no chemical reactions going on. Of course, they're all the same molecules, so they can't. We're going to obey Newton's laws. It seems like a silly thing to assume, right? But when you look at gases like in stars and stuff, these gas molecules are going really fast, and you got to worry about relativistic effects. We're not going to worry about that. We're in slow gases. You know what I mean? Don't worry about relativity. And monatomic. That means all the molecules, they don't have internal degrees of freedom. Now, it's not a very good assumption, but we're going to use it. Like the gas in this room, which is nitrogen and oxygen mostly. What kind of gas is that? Anybody know? It's diatomic. What do we mean by that? Two what? Two atoms. Oxygen comes in a pair, right? O2. Anybody heard of that? Right? We breathe O2, right? Carbon dioxide is polyatomic because there's more than two. It's three. C and two O's, right? Water, vapor, polyatomic, right? Methane, polyatomic. Oxygen, nitrogen, diatomic. But we're going to assume it's like helium. Helium is inert, so we're going to make it easy on us.
You said the molecules don't have degrees of freedom?
They don't have internal degrees of freedom. What I mean by degree of freedom is the way the molecule can move. So our molecules can only move in X, Y, and Z, they don't have any internal vibrations or rotations they can do. That's not true because oxygen, nitrogen does. We're going to make the assumption easy that it doesn't. Okay, make sense to everybody? All right, with that, let's set up our picture. Let's get 2 colors. Okay, let's use all 3 colors today. What do you say? So set up my coordinate system. This is X, this is Y. Here's my container. I'm going to make it a cube for simplicity. Well, it doesn't have to be a cube, but it makes it easier. I'm going to try to draw in 3 dimensions. Not guaranteed it's going to be good. That's not too bad. It's a little short this way, but that's okay. Okay, here's our little molecule, mass m, moving with velocity vx. Of course, we don't have one molecule, we have lots of molecules. Oh, we got it. So, n. N is the number of molecules. Okay, now we gotta go back to physics 1. Are you ready? You ready, Danny? You remember physics 1? Okay, this molecule moving, it has momentum. How do we calculate momentum? Matthew, I can see you're thinking hard.
Don't call me out.
I called you out. Jared. Somebody, how do we calculate momentum?
Is it R times V?
Mass times velocity.
Mass times velocity, not R times V, mv. So this molecule has momentum mvx. Right? Okay. What happens when it hits the wall? We have what kind of collision?
Elastic.
Elastic. What does that mean happens to the molecule?
And
Mhm.
momentum is conserved.
Energy is conserved. That means it bounces off the wall.
It changes the vector, right? Of
Yeah.
velocity.
And it's going to have the same velocity, but in the other direction. Why? Because kinetic energy is conserved. Right? So this is P naught. P final is minus mvx, right? Because it's going in the negative direction. You with me, everybody? Okay, what caused that change in momentum? What causes a change in momentum? This is Newton's second law, so you're obeying Newton's laws. Newton's second law. Anybody?
Force is equals ma.
F equals ma. Or F equals dp dt, change in momentum over time. Right? Anybody remember that? So we're going to use that. So F equals dp dt. We're changing P over changing T. And then P is mv, so we get m delta V over T. That's A. Alright, so that's Newton's second law. So mean of me to pull back physics 1. Okay, so the particle changes momentum. So that means that there's a force on the particle. What's the force? What's creating that force? That changed the momentum of the particle. What was it? What made the particle switch directions?
2mv?
Okay, the change in momentum is 2mv.
Negative 2mv, right?
Yeah.
Is it the normal force?
Yeah, it's a normal force with what?
The box.
The box, the wall, right? Minus 2mvx. That's the momentum change, and it's coming from the wall, applying a force. Let's call this front wall surface A. It hits surface A and it feels a force. I'm going to draw it in blue. Right? That changes the momentum. Okay, you with me? Newton's third law. What does Newton's third law say? Sarah?
The equal and opposite
Equal and opposite what?
reaction.
Okay, reaction, which is what quantity? Say it out loud.
Force.
Force. What does that mean? That means if the wall applies a force to the particle, the particle what?
Apply the forces.
Right, so there's the equal and opposite force applied to the wall. And that's what I want to calculate. Let's call that F. So this F, well, it's equal to what? Change your momentum over some time interval, delta t. So the force on the wall is going to be opposite, it's going to be positive because it's pointing out. Right, so the force on the wall, we'll call it Fw maybe, is equal to the change in momentum over some time interval. So that's 2mvx over some time. Okay, oh, we gotta get how do we get time in here? Well, this particle is gonna keep hitting that front wall, right? And if I kind of want to average that force over collisions, I need to know the time between collisions. So how long is it till that particle hits the front wall again? Well, the particle hit the wall, what's it got to do? It hits the front wall, and then what happens? It moves back, hits the back wall, and then moves back, and then it hits the front wall again. That's the time I want. The time between collisions of the front wall. So what is that time? Well, I got a velocity, and I got a distance, right? So my velocity is Vx. Remember, velocity equals what? Distance over time. Everybody remember that? Physics 1? So, what's the distance I gotta travel between collisions?
L.
Close. I gotta go there and back.
2L.
2L. 2L over T. That's the time in between. Right? So I can solve for V. I can solve for T. So delta T equals 2L over Vx. That's the time between collisions. So I put that into my equation, I can calculate kind of the average force on this wall from the particle hitting it over and over and over again. Right? What's the force felt from that particle? 2L over Vx. The 2's cancel, and I get an m Vx squared over L. Okay, you with me? So bam, the particle's hitting the wall, hitting the wall, hitting the wall, right? Over and over again, so applying this force. Okay? Okay. That's just one particle. The average particle, right? But how many particles do we have?
10 to the 23rd.
Yeah, n, a large number, n, right? And so how do I get the total force acting on the wall? Well, I take the average force times the number of molecules. So the total force on this wall, Ft, is going to be n Vx squared over L. Okay, you with me? I just multiply by n to get the, I took the average times the total number to get the total force. Okay? Now, we didn't get to talk about fluids. We ran out of time because we did so much reviewing, which was good to review. We missed that chapter. But in fluids, we talk about pressure. And now we need pressure for gases. So, anybody know what pressure is? Have an idea what pressure is?
Like the formula?
Yeah, a formula, a concept, units, ideas of what it is. Okay. Huh?
Mass.
No, not mass. Good try.
Times.
Suspension.
Say you're going out to dinner, right? Going out to dinner. You got a nice ballroom, and someone in an evening dress steps on your toe in their high heels. What happens?
Hurts.
That hurts. Why does it hurt?
Pressure.
Okay. What about pressure? Yeah, you're right. Pressure.
The weight is concentrated on a small piece.
Yeah. So pressure is force per area. So when they step on you, all that weight is on a little point. That hurts. Or if it's a big, tennis shoe, it's spread out. It doesn't hurt. So pressure is force per area. Right, and we want to apply that to the wall. Because I don't measure the force on the wall, I measure the pressure sensors. Okay? So, how do we get that? Well, what are the units here? What's the units for force?
Newtons.
Newtons. Good. You guys remember. Units for area.
Meter squared.
Meters squared. We're going to call these
Pascal.
Pascals. Yep. Those are the units we're going to use. There are other units you'll come across in chemistry. Millimeters of mercury to measure atmospheric pressure. Torrs.
What is that? A P and then what?
PA for pascals. So those are the units we're going to use. But it's force per area. So I want to get the area in here. So I'm going to divide by the area. What's the area of the side of the wall?
L squared.
L squared. So if I divide this side by L squared, I divide that side by L squared. So what do I get? L squared times L is what?
L to the 3.
L squared is the area
L to the third.
times the length.
L cubed.
L cubed, which is the volume. Right? So I get N M dx squared divided by, I'll put wings on V. So you know it's the volume, not velocity. Okay, divided by the volume. Make sense to everybody? You with me, Jared?
Yep.
Okay. Let's bring the V to the other side. This is what? This is pressure, right? This is pressure. And then I bring the V over, so I get P times V equals NM Vx squared. That's kind of starting to look like the ideal gas law. PV equals nRT. Well, I'm getting there. I got PV. I got the left side. Right? I got to work on the right side now. Okay. Well, this is the velocity in the x. Right? What about y and z? Right, this particle is moving, could be moving in all three directions. I just picked x, right? So really, I need to consider that. And if you're thinking nRT on this side, I got to get, what does t measure? What does t measure? Anybody? What was t a measurement of, we say?
Temperature.
Yeah, right. So temperature is a measure of what of a system?
Agitation of the molecules.
Agitation of molecules or the random kinetic energy? Anybody have that in their notes?
Yep.
So it's the random kinetic energy. Okay. Danny, what's the formula for kinetic energy? Close, yeah, really close. She's missing one term. It's mv squared, but you need a half mv squared, right? So I want to get the kinetic energy in here, but I only got Vx. But I need V, magnitude of vector. How do I get a magnitude of a vector? Right? If I got a velocity vector and I want it squared, to get the magnitude, what do I gotta do? I gotta add the
Square root.
well, you take the square root, but I'm going to leave it squared, of the components,
Yeah.
right? Pythagorean theorem. So Vx squared plus Vy squared plus Vz squared, right? I want to get the whole velocity vector in here so I can replace this with kinetic energy. Okay, so I only got Vx. How am I going to deal with this? Because I want V, not Vx. Right? Vx is just a component. This is where I use another one of these. So if we use Newton's laws, we don't. I've used this one I'm telling you. All the gases are the same because I only have one M. I have done different M's. We've ignored the size of the molecule. So we've used a lot of these. We've done elastic collisions. We're going to use this one here. Space is isotropic.
Because they're all the same, right?
They're all the same. On average, they're all going to be the same on average, right? So Vx squared, Vy squared, Vz squared are all the same. So I can say that V squared is equal to 3 Vx squared. Right? Because X, Y, Z. So then I can replace Vx squared with V squared over 3. And so the magnitude of velocity squared over 3. Okay, we're real close now. We got an mv squared. We just need, Danny, the thing you missed earlier. The half. We just need the half. Let's put it in. What do you say? How do we put in a half? Well, if I put a 2 in the denominator, what do I gotta do in the numerator? Put a 2. So I just multiply the 2 over 2. Now I have 1/2 mv squared. That's the average kinetic energy. So I can write P times V equals N. And I got a 2 over 3. And then I got a, I got an mv squared over 2, which is the average kinetic energy. Right? Does that make sense to everybody?
Wait, can you write out like how you got from that to the KE?
Yeah. So,
Gotcha.
mv squared over 2.
Okay.
Right, and then I'm left with an N, a 2, and a 3. Okay, so we're making progress here. All right, so we said before that temperature measures the average random kinetic energy. So let's see how that works. So the assumption we're going to use, and I'm just going to give it to you. Erase this. KE is going to measure the average energy. It's going to be 3 halves little kt. So little k is called the Boltzmann constant. It's 2 n's there. And it's equal to 1.3807. There's more, but we'll just round there. Times 10 minus 23rd joules per Kelvin. It shows up, the Boltzmann constant shows up a lot in chemistry, but it also shows up on any time you're dealing with molecules on that size and things. What does it do? Look at the units, joules per Kelvin. Right? What do we say temperature measures on Monday? The random kinetic energy, right? But we don't measure temperature in joules, we measure it in what? Kelvin. So the Boltzmann constant is really a conversion between joules and Kelvin. Right, everybody see that? It connects joules to Kelvin. So this thing we measure Kelvin, which we're used to calling temperature, you could measure it in joules using the Boltzmann constant. It's just a conversion. So that's what that does. It converts the temperature to Kelvin. The 3 halves, that comes from the 3 degrees of motion. Up, down, left, right, forwards, backwards. So that's why there's a 1/2 for each direction. So that's why we get the 3 halves. So we put that in. Put all this in. I'll erase this here. And we'll get the ideal gas law as you've seen it.
Are we gonna need to memorize that constant?
No, I'll give it to you. I mean, you need to know its purpose.
Yeah. Or the number itself.
Yeah, but the number itself I give it to you. So we get PV equals 2/3. I just put the 2/3 first. N. Now in KE, I have 3 halves little kt. And the 2/3 and the 3 halves cancel, so I get PV equals NKT. You say, Dr. Browning, that's not the ideal gas law. What was the ideal gas law that I started with?
PV equals
PV equals little n.
nRT.
Dr. Why am I lying to you? What's the difference?
R.
These are both true. R was the ideal gas constant. K is the Boltzmann constant. What's little n?
Moles.
Moles. Big N is molecules.
Oh.
Yeah. The ideal gas constant is basically Boltzmann constant in moles. Right? So you can do your equation in molecules, you can do your equation in moles. If you look at this, T's are the same, so that means NK equals NR. All right?
What did you say R was?
R is the gas constant. And it's just because chemistry likes to do things in moles. So they use R instead of K. If you do molecules, you use K. If you do moles, you use R. There's a relationship between them. It's on this paper. K, the Boltzmann constant, is equal to R, the gas constant, which is like 8.3 something. I forget what it is. We can look it up when we need it. Divided by Avogadro's number. And it is what? 6.022 times 10 to the... Oh, look at that, look at that. 10 to the 23rd, divide 10 to the... See? And this is like 8 something. So it ends up being like 1.3, so still works out. So this is if you use molecules, R is if you use moles. Okay? Alright, so they're the same. They're the same equation. Right? Just different units.
What's Na again? Molecules?
Avogadro's number.
Oh, there you go.
So that's
Constant.
yeah, constant. That's how many molecules are in 1 mole.
And that's the K equals R over Avogadro is the conversion between
Right, between
the Boltzmann constant.
Boltzmann constant and the gas constant.
and the gas constant.
Okay. We got just enough time. Let's look at this molecules. Because we said, we're using the average and we worked that out and everything. But that means some molecules are moving fast, some molecules are moving slow. Right? And so we want to look at that.
Do we need to know that conversion? Or are you going to have us doing it in molecules?
That's kind of, I wish we could all do molecules, but a lot of the stuff is done in moles. So we got to be able to switch between.
Okay, so know
So you're
that,
going to need to know how to convert.
know that conversion.
Yeah.
What about this right here? Like Ke equals 2/3.
Yeah, you should know that.
Know that.
3/2. Yeah, because that's if I give you the temperature of a gas, you can tell me what the energy of the molecule is. You see what I'm saying? So that's pretty important.
You said you'd give us Boltzmann.
Yeah, I'll give you Boltzmann constant. And I'll give you Avogadro's number, even though you should know that. But in chemistry, they're not going to give you Avogadro's number.
That one's in my head somewhere.
Yeah, buried in there, right? From high school. All right, so let's look at these molecules, moving fast, moving slow. See what that looks like. Okay, so here, you can see the molecules are moving fast, moving slow, right? This is the distribution. Everybody know what I mean by distribution, right? So it's showing me the number of molecules at each speed, right? Normally when you think of distributions, you think like distribution of grades. And that follows ideally what? I mean, it doesn't always, but you get the bell curve. Remember heard of the bell curve? And what do you know about a bell curve?
The highest point in the curve is the average.
The highest point is the average, right? Yeah, so the highest point is the average, and it's symmetric on both sides. This curve is not the case. All right, it doesn't follow it's called the Boltzmann distribution because it's a different curve. I'll show you another graph that gives you a little more finer detail. This is if you graph it out. This is the formula for it here. So it depends on temperature, it depends on mass, it depends on the velocity, right, at each velocity. So each velocity, here's the velocity down here, here's the number of molecules. For a total number of molecules, I forget how many they said in here. We can look at the constants. But we're having an atomic weight of 131 and an average temperature of 547 Kelvin. This is what the curve looks like, right? And it's not symmetric. Right, because from here to the peak's around just under 300, right? To get from 0 to the peak. That means it should come back to 0 at, if it was a bell curve, at what? 600. But notice this keeps going. So this Boltzmann curve, it has a longer tail on the fast side compared to the slow side. So it makes it not equal distribution. So the peak isn't the average because this tail is pulling up the average. Okay, make sense to you guys? I'll give you some formulas. You don't have to memorize them, but they're worth understanding the idea. Let me change the temperature and you can see how it changes. But you can see the tail changing there, or if I make it very narrow. Right, let's zoom it out a bit. Now, you can see the peak's somewhere over here under 200, but yet we're going up here to 500 something. So you see that that tail is pulling the average up. Put it back. So what does that mean? This point here, right, this is the peak. Right, so I'll try and draw that there. So that's somewhere roughly there, right? That's the peak. How do I get the peak? Well, I would take this function, take the derivative set equal to 0, solve for v, that would give me the peak. That's the most probable. B, I'm going to call it NP for most probable. And the value of that is, I have it in my notes. You don't have to have these memorized, but they're worth understanding the idea. It's equal to 2 KT over the mass, molecular mass. Right, so that's the most probable. So if you were to grab any molecule out of the gas, it would probably have this velocity. Now the average is where? It's up here high, right? And what's the average do? You add up all the molecules and divide by the number, right? So basically you're finding, you know, half the areas on that side, half the areas on this side of the average. Does that make sense to everybody? Because you're using the area. So it's going to show up here. That's not straight down at all. And I just guessed. I don't know if it's really there, but that's the idea. So V average is square root of, and you could do this, 8 KT over pi m. That's all under the square root. You could basically find the area of the curve, find where half is on one side, half is on the other, and you can calculate.
You have to integrate, right?
Yeah, you'd have to integrate. Yeah, you'd have to integrate this, which is a little messy.
Using Riemann sims.
Yeah, I think you could actually work it out exactly, but you
A
could
little
do the rest.
messy is crazy.
What?
It's a little messy.
A little.
A little messy, right? But the one we're interested in is called VRMS, which is here. And VRMS stands for root mean square. And we'll see why that one's important, but that's equal to 3 KT over M. Now, how do I get VRMS? VRMS, what I would do is I would take the square root of the sum of all the velocities of all the molecules and then divide by the number of molecules. So I equals 1 to n. So I square the velocities and then add them. Now why is that one important instead of just a regular average? Well, what does temperature measure? It doesn't measure the velocity, it measures what? Kinetic energy. And how do I calculate kinetic energy?
Velocity squared.
Velocity squared. So that's why the root mean square is the important one. Because that's giving us the energy.
What is it? Like,
It's 3 KT over n.
no, but like, what would you use that for?
To calculate the average energy.
Okay.
Right? Because the average energy is V
So you would
squared.
just take that that V number and plug it into like just a kinetic energy formula?
Yeah, right. So if you were to use the kinetic energy, you would use, so if you were to use this 3/2 KT, and you say this is equal to 1/2 mv squared, you're actually getting VRMS here. So when you use that, you'll get the average root mean, you get the root mean square velocity, which isn't the average because it's not a bell curve. If it was a bell curve, it would all line up, all three of these. But it's not a bell curve. This is the one that kind of really describes the behavior of the system. You think the average does, but because we're looking at energy as an important quantity, the root mean square is the one that does. And we're going to see root mean square when we get to electronics too. Shows that.
And we don't have to know those.
You don't have to know those, but do know that the most probable and the average and the root mean square they go in order. You don't have to calculate them, but you have to know the trend. Does that make sense? All right. That's enough for today. I'll give you 5 minutes free. What do you say? Don't let other teachers know. Don't think I'm easy. We don't want that.
I saw a bunch of music students walk into your acoustics music class yesterday. I was like,
Oh man, I killed them yesterday. I gave him velocity equals change in distance over change in time, and that just train wrecked them. But they're good kids. But they think they're taking physics. They're not.
My sister thought she was taking physics.
Yeah, your sister, right? She was in Cosmos. She thought she was taking physics.
Did anybody think they were taking an actual like acoustic class? Like
I've had that before. People thought they were going to learn acoustic guitar. I had one guy. He was a senior history major, and the second week of class, he stood in the middle of class. This is not what I signed up for. This is acoustics. I'm supposed to learn the guitar, and he walked out, stormed out, and complained to the dean.
what?
The dean's like, "You're signed up for the wrong class, buddy." It was bad.
That's funny.
So I always tell them now it's not music class.
Oh, our assignment isn't open.
Yeah, okay, well, I got an email on that. So they're having trouble with the books. Any surprise, right?
Really?
Yeah, I got an email saying that it's not, is nobody in, or the assignments aren't in, or?
I just
It's
can't
in.
get to the assignment,
Did those?
right?
Yeah.
Computer science?
Mine
You
works.
said there was like a Cengage issue.
So you can get into Cengage, but you can't get any assignments for anybody?
Yeah, I got it.
You can do
Yeah,
assignments.
I was doing yesterday.
I actually got into the assignment too.
You got an assignment, but Mary, you can't get any assignment.
I also can.
Who has Self or Smart? And all of you have Self or Smart.
Yeah.
They said there was some issue with Self or Smart and the textbook, and they'd have it resolved by next week. That's what they told me.
Okay.
So I will add an extension on the homework, as we need, and let's see if they get it fixed. Let's reconnect Friday on that question.
It just says it's part of an unpublished module, and it's not available yet.
Okay.
It's all I get for the assignment.
I will
Can
ask.
you go in like through Cengage stuff through the book?
Let me
See
show
what I
you.
mean?
I'll have to ask Online Learning because they're the one that connected
Alright.
Cengage to Canvas and put it all together. I just pick the assignments and then they sync it up. So I'll follow up with them. Can someone send me a reminder email to do that tomorrow?
You did it through the book.
To connect with Online Learning about the Cengage Canvas connection.
Cengage and you it's open in Cengage.
And it goes to all the homeworks.
And then you can open the homework?
Yeah, every one of those, even the one due April 20.
I thought you could open them anytime.
Yeah, I have all of those here.
Okay.
Like,
For physics 1, we couldn't. We had to wait until the week.
Oh, you did?
Yeah.
I set them up different, I guess.
do you want me to?
Yes, hit stop.